Hi, everybody. Today is Wednesday, March 6th. We will continue on 9.2 today. Yeah, we'll be high schedule. So the midterm grades is due next week. And then I check your grades. I realized many of you haven't finished all your homework. And some of you missed the practice exam and exam correction and record. So this week, please try to increase your homework grade as much as you can. And also, if you haven't turned in your practice exam correction and record, please turn those in. So I hope those can boost up your midterm grades. So I will submit your midterm grade probably in one day. Okay. So yeah, improve your grades. It's right now. 0 to 50 is F. 60 to 70 is D, and this 70 to 80 is C, 80 to and 90 is B, and then the A is above 90, right? Yes. So if you're in the F range, so do your homework or the self-assessment. I hope that it can help you to improve to the D range. Then our failure rate won't be that high. If the failure rate of a course is high, then somebody will come to us and talk to us. Yes. Okay, so try to increase your homework scores. So let me ask you, it's not just one or two students. Several students get a low grade on the homework. So how do you feel the homework? Do you have difficulties working on the homework?
Yes, some difficulties.
Some difficulties?
Yeah.
When you look at the solution, are you able to understand the solution?
It's not this. It's not the solutions that's the issue. It's when you're trying to do the problem and they have the videos, and the videos sometimes aren't what we do in class. I think that's what's complicated.
Oh, yes. So okay, because sometimes there's more than one ways to solve problems, and I teach you the way I think is easier. So for assignments, I hope all of you. So instead of looking at the videos, look at the solution first because I wrote the solution. So you see all the problems. I give you the detailed solution. And do you realize for many of the problems, the solution and my version of the problem and your version of the problem, some of them is just different. The numbers are different, right? And most of them, the numbers are different. And I work with some of you, and I realize some problem is exactly the same. Have you realized that? So I hope you can look at the solution first. Okay, look at the solution and try to understand the solution, and then you look at your problem, and usually it's some numbers difference. Then you can work on your problem. Okay, and yes, so the video is extra help. Okay, but the first thing, look at the solution and see how I solve it. All right. So promise this week increase your homework scores, and I'm always in my office waiting for you to come to see me, and I have a table in front of my office. So I hope you can come to that table and work on your homework. And if you have questions, just come to my office and ask me, and I can look at your work and tell you, hey, what's wrong? And maybe if you want more information of those type of problems, you can also ask me. Okay? Yes.
When are you in your office?
Today I'm in my office from 11 to 1:50, and afternoon I usually in my office from 3:10 to 5. Monday, Wednesday, Friday. But sometimes in the afternoon I might have meeting. So this afternoon I have meeting at 4. Okay, but 11 to 1:50 is a good time. So and also Tuesday, Thursday, usually I'm in my office from 10 to 1:50. So a long time. So I have a lot of available time in my office. So yes, work hard on your homework And yeah, submit your practice exam correction and wrapper. Hopefully you can increase your grades, your midterm grades. Is due. I will enter your midterm grades on Monday. Okay, so let's continue. So last time we were looking at the partial derivatives. Yes, do you remember? Partial derivative with respect to x. We imagine y is a constant. We differentiate with respect to x. Okay? And partial derivative with respect to y, we imagine x is a constant. And then we differentiate with respect to y. And last time we did example 1, right? The partial x is for the derivative of x cubed is 3x squared. And the derivative of x squared is 2x. And the y cubed is like a number. You multiply the y cubed. Constant multiple stays here. Do you remember, everybody? And the derivative of negative 2y squared is 0. Because it's like a constant. The derivative of a constant is 0. And the partial f partial y, or the derivative of x cubed, is 0. Because x is now a constant. X cubed is also a constant. And the derivative x squared, constant multiple, stays here. The derivative of y cubed is 3y squared. Yeah. The derivative of negative 2 stay here. The derivative of y squared is 2y. So 2y times 2 is 4y. Right? This is last time. And let's continue. So fx, we plug in 2, 1. This means x, we plug in 2. And the y, we plug in 1. Right? So let's see. 3x. What is x? We plug in x's 2. Yeah. We evaluate at the point 2, 1. Yes. So 2 squared plus what is y? 1. So 1 cubed times 2 times x. X is 2. What is 2 squared? 4. 4 times 3? 12. And 12 plus what? 4 is 16. Is that okay, everybody? How about we evaluate the fy at 2, 1? X squared becomes 2 squared, right? And 3 times y is 1 squared. Minus 4 times y is 1. What's 2 squared times 3? 12. What's 12 minus 4? 8. Okay, what does these mean? Okay, so you have your surface, right? You have your surface, your graph, and the derivative corresponds to the slope of the tangent line, right? From calculus 1, we know the derivative is the slope of the tangent line. But like your surface, how do we define the tangent line? Okay, so let me see. Do I have a picture here? Okay, I have a picture here. So what it means, you have a surface. Can you imagine a surface here, right? And the partial f partial x, y is a constant. X varies. Y is a constant. It corresponds to a plane, right? Y equals a number is a plane. So you have this plane is parallel to the xz plane, right? You have this plane. You intersect. You cut the surface. Do you see the intersection is now a curve? It's a one-dimensional curve. Because it's a curve, now you can talk about the tangent line. The tangent line right here. The slope of this tangent line is the partial. So you get partial f, partial x, when you plug in a number, a point, you get a number. That number is actually the slope of the tangent line of this curve. Is that okay, everybody? How about partial f, partial y? See, x is fixed. The y varies. X equals to a number is also a plane, right? And this plane is parallel to the YZ plane. And you use this plane, cut the surface, you get a curve. Right, everybody? You get a curve, so you can talk about the tangent line. The tangent line, you can talk about the slope, and the slope is this number, the partial f, partial y. Evaluate at the points A, B. Oh, here. Thank you.
Also, don't forget to plug in your laptop.
Oh, yes, thank you. I really need that reminder. Okay. Yes, perfect. Thank you. Okay. So, look at the slope. If the slope is positive, what does that mean? Slope is positive. It means when x increases, your height increases, right? If slope is negative, if your your x increases, your height decreases, right? And slope is 0, it means your x as your x increases, your height remain constant. Is that okay, everybody? So we just talk about how the height, the c is changing when you walk in the x direction or walk in the y direction. Okay, good. That's the meaning. Now let's do more examples. Okay, let's do harder problems now. Okay. Again, review. What's the derivative of exponential function? E to the kx times k. And what is the derivative of natural log of x? 1 over x. Right, everybody? Okay, so keep those in mind. Let's do the following. Okay, so partial f, partial x. So we take the derivative with respect to x. Y is a constant. Okay, everybody? Look at the first quotient. X is the variable. Do you see the denominator? They're all about y. They're like numbers, right, everybody? So this is like something and then divided by a number. Do we need quotient rule? No, exactly. We don't need quotient rule. So we have that number, get 1 over y cubed plus 5y, and we take the derivative of this guy. Well, this is a composite function. So chain rule, we let this be u. The e to the u prime is e to the u times u prime. Right, everybody? So that's why this is e to the u. U is 2x minus y. And times u is 2x minus y prime. And this prime is taking the derivative with respect to x. So keep that in mind. Right? So this is just a number. We copy down the number. And this is e to the u. The derivative of e to the u is e to the u times u prime. But this prime is taking the derivative with respect to x. Okay? That's the first term. Second term. I have x times something, but this something has no x in it. It's like a number. What's the derivative of this? What's the derivative of x? just 1, right? So the derivative of this guy is just this number, 1 times this number. This constant multiple stays here, right? Plus 1 times ln 7y plus 4. Okay, we're not done because we have still one factor we need to differentiate. What's the derivative of 2x minus y? Derivative of 2x is 2, right? Derivative of 2x is 2. Derivative of minus y is 0. Not negative 1, because y is a constant. Is that okay, everybody? This is 2. So therefore, you can rewrite it. You can move the 2 in front of the exponential function. And denominator y cubed plus 5y and plus, this is natural log of 7y plus 4. So this is the partial derivative with respect to x. So every step you have to remind yourself, what is the variable? What is the constant? Okay, so treat that variable as a constant. Then here you don't need quotient rule or product rule. No, this is just a number. Is that okay, everybody? Now partial f partial y equals. Now we're taking the derivative with respect to y. Look at the first term. What happened? See, I have y in my numerator, and I have y in my denominator. This is really a quotient, right? So we need quotient rule in this case, right? So quotient rule. What's quotient rule again? Yeah, u prime v. By the way, this prime is now with respect to y. Okay, everybody? We write down the quotient rule. The prime now is the derivative with respect to y. So u prime v, and then what? Plus or minus? Minus u v prime. And then all over v squared. Is that okay, everybody? The quotient rule. U prime v minus uv prime over v squared. And the prime, in this case, is the derivative with respect to y, not x anymore. X is a constant. Y is the variable. Next, second term. X is a constant, a number, right? So when you differentiate this, the x is a number, it stays here. And yes, questions so far? All good? Okay. So we plus x is a number, stays here. Then derivative of ln, what happened? This is a composite function, right? So derivative of ln u is what? 1 over u times u prime. Yeah, so 1 over u, what is u? Yeah, 7y plus 4 times u prime. Is that okay, everybody? We look at the formats. Keep in mind, which one is the variable, which one is the constant, and then we determine what rule to use. Okay? Quotient rule. Chain rule, write it down. Yes. Okay, now we continue. See? Chain rule again, right? E to the U prime is what? E to the U times U prime. But here, this prime is with respect to the Y. Yes, that's why every time I put the prime, I mean the first time I put the prime, I make a note here. This prime is respect to X. Here, this is respect to Y. Now, could you tell me what is this guy? Exactly. Yes. X is constant, Y is variable. So this is actually -1. Yeah. And then minus e to the 2x minus y times. What's the derivative of y cubed? Yes. Plus. Yeah, good. And then all over this. Is that okay, everybody? And plus, okay, cx is in the numerator. And what is 7y plus 4 prime? Or 7y plus 4 prime? Yes, I forgot that. Yeah, see, I also make mistakes too. Gotta be careful. Thank you. Okay, let me move this to the right. So I have some space. Yes. Y cubed plus 5y. Yeah, when the problem get more complicated, and then we have to check one by one. This term is this guy, and this factor, don't forget that. And minus this is here, this corresponds here, and over that, yes. And then the derivative of 7y plus 4 is 7. Okay, that is 7. All right. Is that okay, everybody? Mm-hmm. Yeah. So you can write it down one more line and replace this guy by minus. Yes. But you know the answer? Is that okay to like stop here? Mm-hmm. Yeah, this guy replaced by minus 1. Okay, so this is example 2. Okay, when we have z is a function of x and y. Okay, next example. What if we have a function of x, y, and z? Well, the graph is actually in R4. We cannot quite draw it, okay? But we can still find the partial derivatives. All right. Can you imagine that this guy is going to be in R4? At any point, like here, the x, y, z is in space, and you put this point in the function, you get a number. You can imagine this is like a density of a solid. So you have your domain, x, y, z, is in R3, right? That's your domain, is in R3. So it's like a solid. And then every point inside a solid, you can talk about the density function. Okay? So every point can have a different density. Or if you don't like density, how about temperature? Imagine our Earth. Okay, the outer surface, the temperature is cooler, inside is hotter, right? So every point has a temperature, a different temperature. Yeah. And now, what's the partial derivative? So what's x? That means if you go to so you stand in a point, if you go to the x direction, will the temperature increase or decrease? That's what it means. How about partial f, partial y? You go to the y direction. Is your temperature increasing or decreasing? It depends on whether xy is positive or negative. If it is positive, the temperature is increasing. If it's negative, the temperature is decreasing, right? And fz, you go to the z direction and you think about how the temperature is changing. Is that okay, everybody? This is the meaning of it. Now, take the partial derivative. X is the variable. Y and Z are constants. Look at this. X is the variable. So this is like xz plus 3x squared y. Square root is like to the 1/2. Right, everybody? This is a composite function. We let the inner function be u. What is the derivative of u to the 1/2? So what's the derivative of u to the n? Power function. N times u to the n minus 1 multiplied by u prime. Yes. So this is u to the 1/2. What's the derivative of u to the 1/2? Yes, 1/2 u. U is xz plus 3x squared y to the negative 1/2. And then times u prime. So copy down the u and then prime it. And this prime, we're taking the derivative with respect to x. Is that okay, everybody? That's the first term. How about the second term? Just a number. The derivative of a number is 0. Yeah, exactly. So that's 0. How nice. Okay, so we get 1/2, and this is xz plus 3x squared y, and minus 1/2. Now, what's the derivative of this factor? Yes, z is a number, right? Derivative of x is 1. So z plus 6x y. Because y is a number. Constant multiple stays here. The derivative of x squared is 2x. 2x times 3y. 6xy. Is that okay, everybody? Alright. Bless you. This is fx. How about fy? Okay, fy. We're gonna take the derivative of the first term. U is chain root, right? We actually have the same thing, but the prime now is respect to x. Sorry, not x. It's respect to y, right? Yes. Okay, 1/2 u to the negative 1/2 times u prime. But this prime is respect to the y. And that's the first term. Even though it looks like we write the same thing. That's why I suggest you every time you do the prime, put a small note there. Is this respect to x or respect to y? Then you know the difference. Okay. Yeah, exactly. So this is another chain rule, right? And what's the derivative of negative e to the u? Negative e to the u times u prime. Right? So three type of function we learned: the power rule, the exponential function, and the derivative of natural log of x is one of them. So keep those in mind. You know, all these is just play around with those three-digit formulas. Okay, let's see. Copy it. It has no prime. We copy it. Okay. With respect to y, what's the derivative of xz? 0. It has no y. It's just a number. 0. How about the derivative of 3x squared y? 3x squared. Is everybody okay? The derivative of y is 1. So 3x squared. Okay. If it's multiplication, we don't need a parentheses. Okay, e to the yz. What's the derivative of yz? Do we need product group? No. Is every1 times z. So z is a number, like 2. What's the derivative of 2y? 2. So what's the derivative of yz? Z. Yes. Good job. Okay. That is partial f partial y. Okay. Now let's do partial f partial z. Do you realize the first term is still the same thing? Yeah, 1/2 u to the negative 1/2 times u prime. But the prime is gonna be with respect to z. Yeah. It's still the same thing. 1/2 xz plus 3x squared y to the negative 1/2 times xz plus 3x squared y prime. And what do you say with respect to z? Guess what? The second term, when you take the derivative, is also the same thing, right? It's either the u times u prime, but then here your prime is with respect to z. Yeah. So take the prime in different steps means different things. You gotta be careful. Yeah, it's like changing your role. The XYZ change your role a lot. Which one is a variable? And which one is a constant? Yes, role play. Okay, let's continue. So copy this. We should find one day and you guys become the teacher and I become a student. I sit there and let you, hey, talk about this problem. How to solve this problem. Show me. All right. What's the derivative of xz? X. Yes, very good. Yeah! Just x. That's it. Because the z is only the variable, z is a number, this is a number. And how about the next term? Yeah, it just be y. Right? Everybody? So even though it looks like a lot of variables, but every time you merge yourself, which one is the variable? And all the others is just like constants. Any questions about example 3? No? All good? Okay. And yeah, this picture, and I already explained to you what the meaning of the partial derivative. You go to the x, y, and z direction, and you look at whether your function is increasing or decreasing. And higher order partial derivatives. So we can have second derivative, the third derivative, the higher derivative, and this is, excuse me. This is how we write it. If you use this notation, okay, this notation is like, okay, like the original. Your second derivative, right, is the the d dx of the first derivative. Yeah, everybody? And that's why we put d squared f over dx squared. That's the notation. Because we have 2d, multiply them, d squared. That's the notation. And we have 2 copies of dx. That's why you put dx squared. That was the notation. So here, partial derivative, change the d to partial. So partial, you get partial square f. That's the notation. And partial x squared. But if you use this notation, it's fx. So you look it from the inside to the outside. So you take the derivative with respect to x first, and then the second derivative also with respect to x. Okay? So when you read the order, if you use this notation, you read it from here to here. If you use this notation, you read it from the left to the right. So yeah, x and y, they're the same. But if you do the xy and yx, they're different. If you use this notation, you read it from the right to the left. So this means you take the derivative with respect to x first, and then you take the derivative with respect to y. Is that okay, everybody? So when you use this notation, you read it from the left to the right. You take the derivative with respect to x first, and then the y. Is that clear, everybody? Yeah. Similarly, here, you take the derivative with respect to y first, and then the x. Okay? And this notation, read it from the left to the right. Take the derivative with respect to y, and then the x. You might ask the questions, what if I switch the order by mistake? But is, don't worry, you will get the same answer most of the time. Okay, so we mark the order of differentiation can make a difference in the mixed partial derivatives. But it turns out most of the functions we encounter has the property that the mixed partial are the same. Okay, everybody? It's actually the theorem. So this theorem tells us that if F is defined on an open set, open set means it only contains the interior point. It does not contain the endpoints. Like if in R1, open set like 0 to 1, you use parentheses. This is an open set. It does not contain the endpoint. So it's like you put the open circle there. In R2, maybe I should draw here so your other student can see. So in R1, open set like 0, 1, we use parentheses. It means we don't include the endpoint. Okay? But in R2, open means, okay, now you have an XY plane. So open means you have a region and you don't include a boundary. So if you don't include a boundary, you use dash line, dots, to indicate you don't include a boundary. Okay, if you want to include a boundary, you draw a solid boundary to indicate you include the boundaries. Okay, so this is an open set. It only contains the interior points, not any of the boundary points. Okay, if the function is defined on an open set and the partial derivatives are continuous throughout this set, then they are the same. Okay, so for most of the functions we learned, they satisfy this property. So therefore, fxy is fyx. You don't need to do it twice. Is that clear, everybody? All right. And assuming sufficient continuity, this theorem can be extended to higher partial derivatives. So fxy x, so which means you take the derivative with respect to x first, and then y, and then x. This is the same as fy xx. It's the same as y, x xy. Is that okay, everybody? So the order does not matter. Okay, so example 4. Find all the second partial derivatives. Okay, so let's see. We have fx. How about you tell me the answer one by one? Wait, what is fx? Yes. And then the second term, which is awesome. So this is with respect to x. So e to the 2xy plus 1. What is the derivative of 2xy? Do you bring? Yes, very good. Yes, good job. So this is partial f partial x. Is that okay, everybody? Okay. So everybody finish this step. Well, I'm looking at you in the next step. What's partial f partial y? Mm-hmm. Mm-hmm. Yeah, with respect to y. Ooh, derivative with respect to y is. Do you see any y here? Yes, right. Okay. And then we copy this down. What is the derivative? Good. That's 2x. And that's it. Mm-hmm. Okay, that's fx, fy. Now, all the second partial derivatives is going to be fxx, fyy, and fxy. And you can imagine fxy is the same as fyx. Okay, Gabby. fxx. We take the derivative of mx with respect to x, right? What's the derivative of this? Yeah, u prime is still with respect to x. And multiply by 2y. Yes. Because the 2y is like a number. Constant multiple stays here. Right? Do we need product rule here? No. Right? No need to product rule. Because 2y is a number. And then what's the derivative of 15x squared? Yes, very good. Is that okay, everybody? What's the derivative of 2xy? 2y. Oh, we get another copy of 2y. Therefore, we get e to the 2xy plus 1. 2y times 2y is, 4y squared. And plus 30x. Is that okay, everybody? Mm-hmm. Mackenzie. How about fyy? What's the derivative of this? Yes. And what is e to the 2xy plus 1 is equal to 1? Yes, this becomes. Yes, very good. So e to the 2xy plus 1 times. Yes, good job. Is that okay, everybody? Awesome. And then fxy. Okay. So you have two choices. You can take the derivative of fx with respect to y, or you can take the derivative of fy with respect to x. Which way do you prefer? Up to you. Which way do you prefer? So yeah, fxy is the same as fyx. Fxy means you look at the fx. So you look at this function. We differentiate with respect to y. Or fyx, you look at fy, and we differentiate with respect to x. Fxy, we do this one? We take this with respect to y. Okay, yes, we can do that. So now let me use a different color. Yeah, that one, you get the hardest problem. Sorry. So we look at this guy. Differentiate with respect to y. Oh, you see something times something, and they both have y. What do? Is something times something, and they both have y. You gotta have product rule, right? What is product rule? So product rule, we have two things multiplied together. You remember product rule? U prime is U prime V plus U V prime. The story, you and your friend go to the restroom together, and there's only one toilet, so you go one by one, right? So your U is here. We write down e to the 2xy plus 1 prime. Yeah. And then how about next? What's next? Mm-hmm. Mm-hmm. Good. And what's the derivative of 15x squared with respect to y? Yeah, very good. So this is with respect to y. Awesome. What is e to the 2xy plus 1 with respect to y? Mm-hmm. Yes. And we're taking the derivative with respect to y. And then times. Good job. And what is this? Yeah, very good. It's 2x. Right, everybody? We take the derivative with respect to y. Awesome. Do you see both of them? Both terms have the factor 2xy, e to the 2xy plus 1. Yeah, we can factor that out. And 2x times 2y is, 4xy and plus the 2. So you can rewrite it like that. Yes, so that is the answer. So in example 4, we have two variables x and y, and then you expect a second partial derivative, you get 3 of them. You can actually check to find the derivative like f, y, x, and then you can show they have the same answer. Any question up to now? Okay, Example 5. I know we don't have enough time, but I just want to talk about the setup. So you have 3 variables. So the first partial derivative, you're going to have fx, fy, and fz. Do you agree? But the second partial, you will have fxx, fyy, fzz. Yep. And fxy, it will be the same as fyx. fxz will be the same as fzx. And who's the last one? fyz, it will be the same as fzy. So you have 3 first partial and 6 second partials. You have 9 things. Look, the next class, we'll do this. So please work on your homework and look at the solution and come to see me, ask me questions, improve your homework grades. Because the homework is our foundation, and then the practice exam, and then your actual exam. Bye. See you on Friday. Next class, print out 9.3.
I won't be here on Friday.
Oh, because
I'll be back